Let's work through some of these practice problems here. So starting with this first one, we know that wave pulses on a long slinky arrive once every 3.1 seconds. That is our period there, 3.1 seconds. And we're told the distance between the waves is 3.5 meters. So that is going to be our wavelength. We want to know the velocity. So we're going to use our equation velocity equals wavelength times frequency. So we can say our velocity is going to be this 3.5 times our frequency, but we don't know that yet. However, we do know the period, and with that period, we can find the frequency because we know frequency is just 1 divided by the period. So we can say that frequency is 1 over 3.1, which gives us a frequency of 0.323 hertz. We can then go and substitute that in here. So we're going to say 0.323. And then we end up getting a velocity of 1.13 meters per second. All right, so we're going to move on to this next problem here where we have two different graphs we want to analyze and find everything we can about them. So for this first graph, we're given our velocity is going to be 40 meters per second. The next thing we can do is we can really dive into this graph a little bit here and read some things about it to get additional information. So first of all, we see that here is our peak up here. And so we can say that this distance from equilibrium to the peak will be our amplitude. So our amplitude is going to be 15 meters. We also can look at one wave, okay, and think about what that means. So if we look at our x-axis, we see that it's in units of seconds. And so that means that one complete wave, which would be from here all the way to here, one complete wave is going to represent the period. So this time for the period from here to here is going to be 1.5 seconds. And if we want to verify that, we can see that we actually have two waves occur at 3 seconds. I know it's in between, but we can verify that it is truly 1.5 seconds. So that's going to be our period there. From there, we can go ahead and solve for a few other quantities in our problem. The first one we can find is the frequency. We can say that frequency is just 1 divided by that period. So when we do 1 divided by 1.5, we get a frequency here of 0.67 hertz. So that one we can fill into our chart here. The other thing we can find using our other equation is we can find the wavelength. So we can say velocity is just wavelength times frequency. We know our velocity is 40. Our frequency we just found to be that 0.67. So when we go to solve for our wavelength, we get that the wavelength here is going to be 60 meters. And so there we have our chart with all of that information. We can now move on to our second graph here. And in this case, we're given the period. So that one we can go ahead and fill in. Our period is going to be 0.4 seconds. We also can get some information from this graph as well. So once again, we'll look for our amplitude, which would be the distance from the middle to a peak, which is right here. So it's not an exact value here. It doesn't look like it's completely in between, but we can say that this is going to be about 220 meters, 220, 225, something like that. We also can look to get, since our x-axis here is in meters, 120 meters all the way out there, we can look to get our wavelength. So if we think about one complete wave, that would be from here to there. And it looks like, again, kind of going forward, two complete waves happens at 20 meters. So this distance from the start to where that wave starts repeat itself is going to be our wavelength, and it's about 10 meters. So we can go ahead and fill in that information in our chart here. So 220 meters for our amplitude, 10 meters for our wavelength, and we once again can do a little bit of math. We can say our frequency is 1 over our period. So in this case, 1 divided by 0.4, and we get a frequency here of 2.5 hertz. And then we can go ahead and solve for our velocity by doing velocity is wavelength times frequency. Our wavelength is 10, our frequency is 2.5. So we end up getting that the velocity here is going to be 25 meters per second. Our next problem is really just a conceptual question. We want to know how can you change the velocity of the wave, and there's really only one way to do that, and that is change the medium. You have to change something about what the wave is traveling through. Certainly depending on the kind of wave and what the medium is, you could think of some specific examples, but that is the big overarching idea. All right, so for this next bit, we're going to work through these different descriptions and state which of the four shun words, which we see over here, is going to relate to each of these examples. So we'll start with this first one for A. You fix your hair while looking at yourself in the mirror. While you're doing that, you're looking at your reflection in the mirror, so that would be an example of reflection. The second one, a projector creates an image of a slide on a screen. We didn't actually talk a ton about this. This is getting a little bit more into the optics unit, but when light is going through the projector, it travels through something called a lens, and that bends the light and focuses it. So that bending is an example of refraction. For the next one, when a teacher's door is open, you can hear the teacher down the hallway. That's because that opening in the door, when the sound waves hit that opening, they don't just go straight through, they spread out, which we refer to as diffraction. So this would be an example of diffraction. For the next one, light going through two slits creates an interference pattern because the light from each slit adds together or cancels out. That should be the key part there. That tells us this is an example of superposition. Okay. Spear fishing is difficult because the fish is not where it looks from above the water. So if we have some water here and we have a fish underneath that water, okay, what ends up happening is the light waves from the fish hit the water and then they bend, leaving that water. And so the fish does not appear to be where it is because these light waves are bending. That's an example of refraction, once again. For the next one, your cell phone works because the signal can bounce off of a satellite. The idea of light or any wave bouncing off of an object is an example of reflection. Okay. In the mountains, you can still hear the radio even though the mountains block the tower. This one maybe requires a little bit more thinking here, but here is your radio tower giving off waves, and here's your mountain in the way. What ends up happening, though, is the waves bend as they go through the mountains. That's an example of diffraction. Okay, it's not just necessarily spreading out through an opening, but spreading out around barriers as well. The next one, ocean waves bend as they are breaking on the shore. The bending is the key part here. Anytime a wave is bending or changing directions, that's an example of refraction. And lastly, when two waves collide, they make a huge wave. Those waves are combining to make a bigger wave. That's an example of superposition. For this next question, we just have some basic ideas about sound waves. So what do we need to change about a sound wave to make it louder? How loud it is relates to the amplitude. We would need more amplitude. To make it deeper, that relates to the frequency, the pitch. Depends on the frequency. And how do we make it faster? Once again, the only way to change the speed of a wave is to change the medium. So for this question, we have a Doppler effect problem. The reason why we know that is we have both objects moving, and the one object, Bobby, lets out a scream at a frequency of 488 hertz, and we want to know what frequency is heard by the running back. So we're going to start with our equation for the Doppler effect, which is the frequency observed equals the frequency of the source times V plus or minus VO all over V plus or minus VS. And so we have here 10 meters per second. That is the observer in this case, the running back, so that's going to be VO. And the 14 here will be VS. And then, of course, the 488 is the frequency of the source. So we can say the frequency observed will be equal to the frequency of the source, which is 488, times V, which we know is 343. That's the speed of sound in air. Unless otherwise specified, you can assume that that V is always 343. So I'll actually fill that in for both the top and the bottom of this fraction here. And then the velocity of the observer is going to be 10. The velocity of the source is going to be 14. I'm intentionally leaving out the plus or minus for now because I'm going to think through this process. I know that they are running towards each other. And what I always remember is that running towards each other leads to an increase in the frequency. And so what I'm going to do is I'm going to add that number on top to make the top of the fraction bigger. I'm going to subtract the number on the bottom to make the bottom of the fraction smaller. And so I can say the frequency observed is going to be equal to 488 times 353 divided by 329. And when I go ahead and solve for the value of that frequency, I end up finding that the frequency observed is going to be 524 hertz. All right, so for this one, we have another Doppler effect problem. In this particular case, we have a police officer driving away from a stationary person. The police siren lets out a frequency of 850 hertz, so that's the frequency of the source itself. But the person only hears a frequency of 770 hertz, so that's the frequency observed. It is important to note that the person, who is the observer, is stationary. So we can say that V0 is 0, and we're trying to figure out the speed of the car, which would be the velocity of the source. So we can begin here with our Doppler effect equation. Frequency of the source, or frequency observed, equals the frequency of the source times V plus or minus VO, all over V plus or minus Vs. So we can go ahead and fill in the things that we know here. The frequency observed is going to be that 770. That's equal to the frequency of the source, which is 850 times V, which in both cases is this 343. And then the velocity of the observer is 0, and we're trying to find the velocity of the source. Now, in this case, we are moving away, so we're going to keep in mind that when we are moving away, that leads to a decrease in our frequency here. So what that means in terms of our signs, the plus and the minus, is we are going to subtract on top, not that it really matters because it's 0, and add on the bottom. And so what I end up getting is 770 is equal to 850 times 343 over 343 plus Vs. I'm going to go ahead and multiply the top parts here, the 850 and the 343. And so I can say that 770 is going to be equal to 291,550 all over 343 plus Vs. At this point, I would go ahead and cross multiply. Okay, I'm not going to actually distribute that. I'm just going to say 770 times 343 plus Vs equals 291,550. I can then divide by that 770, and so I end up getting that 343 plus Vs is equal to 378.6. And I can go ahead and find the velocity of the source, and I find that the velocity of the source here is going to end up being 35.6 meters per second. So we're going to move on and start doing one related to music and the harmonics and resonance frequencies heard from musical instruments. So for this one, we have a clarinet that operates as an open-closed pipe, which means we're considering the equation L equals m lambda over 4. And keep in mind, in this equation, m, your harmonic numbers, are only the odd numbers here. And so the length of the pipe when the keys are pressed is this 0.267 meters here, and we want to find the first 3 harmonics. So for those of you that are visual people, what those first 3 harmonics are going to look like is shown over here. So this would be the first harmonic where we have 1/4 of a wavelength, the third harmonic where we have 3/4 of a wavelength, and the fifth harmonic. And so we're going to go ahead and sub in those numbers and find those first 3 harmonics. So the first thing I'm going to do is find the wavelength of them, where standing waves will exist. So we can say 0.267 equals 1 times lambda over 4. So for that first harmonic, we have a wavelength of 1.068 meters. For the next harmonic, which is going to be a harmonic number of 3, we can say 0.267 is equal to 3 lambda over 4. So we multiply by 4 and divide by 3, and we get that lambda for that third harmonic there, which is the second one we hear, is going to be 0.356 meters. And then lastly, for that final harmonic, which is the fifth harmonic, we can say 0.267 is equal to 5 lambda over 4. So lambda in this case ends up being 0.213 meters. From there, we can go ahead and determine our frequency. So we're going to go back for each of them and say v equals lambda f. In this case, our velocity will always be 343 because it is traveling through air, so that's going to be the speed of sound through air. So we can sub in our wavelength and determine our frequency. So for the first one, the frequency is going to be 321 hertz. For the second one, our frequency is going to be 963 hertz. And for our final harmonic, that fifth harmonic, which is the third one that we hear, our frequency is going to be 1606 hertz. And there we have it for the first 3 frequencies that are heard. All right, for this last one here, we have another music problem. In this case, we have a guitar string which is closed or fixed at both ends. What it would look like when that standing wave is created is something like this, just oscillating between those two states. And so when that's true, we're going to use this L equals m lambda over 2, and here m is 1, 2, 3, and so on. So the first thing we want to find is the fundamental frequency in this case, and we remember that fundamental frequency means that m equals 1. It's that first harmonic there. And so what we can do is we can put in the length of our string here. We know that that m is going to be 1, and we can go ahead and solve for lambda, and we end up getting that lambda is going to be 1.6 meters. That's our wavelength. And from there, we can use the velocity of waves on this string. We're not using 343 here because it's not traveling through air, it's traveling along a string. And so we can go ahead and calculate that frequency. And so we end up getting that the frequency here is 196 hertz. Moving on to part B. For part B, we want to know what length we need in order to play this note here of 220 hertz. So I'm actually going to start with my velocity equals wavelength times frequency equation. Our speed is still the same because even though we might be changing the frequency, we haven't changed the medium, and that's what's key in order to change the speed. We don't know our wavelength now, but we do know our frequency is this 220 hertz, and so we find that our wavelength in this case will be 1.425 meters. From there, we can go ahead and solve for the length of the string by doing L equals m lambda over 2. We're still talking about the fundamental frequency because we're still concerned with the frequency that we actually hear of 220 hertz. Our wavelength is this 1.425, and then we can go ahead and get our length, and we end up getting 0.71 meters would be the length of the string in this case.